All right, so we're in the middle of talking about the theory of weak lensing, and I showed you these maps, this simulated map of the kind of signals that we expect. It shows the density of the mass density in blue, with the light blue corresponding to overdensities and the dark blue corresponding to underdensities. And the shear is shown as these line segments here, which characterize the distortions that galaxy images would be subject to if they were placed behind, if the galaxies were placed behind these structures. Now let me say a little bit more about these simulations, how they're done, because it also illustrates the process of nonlinear structure formation, which is what we're probing in the weak lensing and in large-scale structure surveys in general. And also that way it anticipates on Anjan's lecture, which will give you all the theory behind it. So in order to do this, let me tell you a little bit how these, the different stages in the simulations. So basically the first stage is to run an Endbody simulation, which is basically a simulation where one puts some dark matter particles in a box. So this is an example from the group in Chicago. So there's a box. What you'll see is the way these dark matter particles distribution evolve as a function of time. This starts from very high redshift of about 30 or so. So these particles are put in a box. Then some of the density perturbations are for the initial conditions are put in by displacing the particles a little bit, so that the power spectrum of the density is what is expected at that redshift for in the linear regime in that given cosmological model, which is being considered here. And then basically we turn on gravity, and the particles start moving, and the structures start forming. Now the box here is in co-moving coordinates, so even though the universe is expanding, the box here is plotted in such a way that it doesn't change with time, but the expansion of the universe is taken into account in the simulations. So when this is done, I'll show you a movie of how the particle distribution evolved. Okay, so you see, first you have some small perturbation that you can barely see by eye, and as time increases, you see more and more structures forming. So the overdensities corresponds to clusters of galaxies and groups of galaxies, and you also see filaments which are connecting the different clusters. Maybe another way of looking at it is they have a version of it which is with a rotation. So it's the same simulation, but now the box is going to be rotated to help us visualize the different structures. So here you see the box is rotating, and at first the density fluctuations are small, but as time evolves, the gravity, basically the action of gravity, so the only force acting here is gravity, it's only dark matter particles here, then the structures start forming at higher and higher contrast. So let me show you again. You see they start forming, and you start forming this filamentary structure, which sometimes is called the cosmic web, and that texture with filaments and clusters and clumps, halos at the intersection of filaments is characteristic of structure formation when only gravity is acting, and in particular in cold dark matter models, this is the type of structure that one expects. Okay, so to do these lensing calculations with the shear maps I showed you before, what people do is that they run Endbody simulations like this. So they evolve it in time by putting the right initial condition, the right expansion history, they turn on gravity, the particles form structures, and then what they do is they shoot artificial photons through the box. Of course, they do it also as the box is evolving, so they do it actually through a light cone that they reconstruct from the simulation. So they shoot artificial photons, they make them deviate from a straight line according to the theory of weak lensing. So basically they can compute the gravitational potential, and they see how the particle trajectory gets deflected by the density, by the gradients of the gravitational potential. And at the end, what they get at some plane, which they consider to be the observer, at the location that they consider to be the observer, then what they get, they look at what the displacements of the photons are, and from that they can get the measurement of the simulated of the shear for this simulation, and they can also project the density contrast, and they get a projection of the mass as well. Okay. So you see, this is the way basically the structures form, and from which how we can get these lensing distributions. So one thing I want you to say before we move on is that in these simulations, at first, the density contrasts are weak, so we can use a linear perturbation theory to describe it. But as you see, as time goes on, the structures become very nonlinear. Basically, what you see is collapse of structures. And so there, linear perturbation theory does not apply anymore. And that's why we use Endbody simulations to simulate these structures. And what you get is structure with this texture, which means that they no longer have Gaussian perturbations. So at early times, when you're still in a linear regime, people think, and there are good constraints on that observationally, that the initial perturbations are Gaussian or close to Gaussian. So it means that the joint density, the joint probability distribution function between any 2 points or many points in the universe is Gaussian, which means that all the information is encoded in the 2-point function of the power spectrum. But as time goes on, the structures become non-Gaussian, and one needs more than the power spectrum to characterize this texture of this structure. Okay, and I'll come back to that later when we see how we can characterize the lensing field, and in particular statistics beyond the 2-point function.
So you're not considering dark energy in the simulation?
So the dark energy is included in the simulation because in the way the universe expands, so the dark energy in these models only affect the rate of expansion, and the rate of expansion assumed for the simulations includes dark energy.
Even structure formation will depend upon dark energy?
Yes, it will. Because see, here we're plotting it in co-moving coordinates, so the box doesn't change size. But if you plotted this in physical coordinates, the box will be expanding, and the rate at which it expands will depend on the amount on dark energy. It will be affected by dark energy.
You're taking that as homogeneous?
We're taking in these simulations, the dark energy is assumed to be homogeneous and only affect the background expansion. But if you change your dark energy model, then the background expansion that is assumed in the simulation will be different. That it would change the way these structures form. As I said, the structure formation, the structure formation is basically can be thought of a competition between gravity that tries to make these structures form, and the expansion, we try to pull the structures apart and keeps them from forming. So if you add more dark energy, what happens is that the universe is accelerating faster, and so the structures form, the rate of structure formation goes down. So you form less structures or less dense structures. So as you change the dark energy, that would change the statistics of these structures. So it is taken into account the simulations, but only as a background expansion.
If you take quantum dark energy and along with background, will affect this?
Yeah, so it depends on your model of dark energy, okay? But there are models of dark energy where you have perturbations in the dark energy, but these tend to be on very, very large scales. And on the scales that we're looking at here, it would not have any effect. But on very large scales, you have changes in the, it affects the structures on very large scales. And that can also could be taken into account, but in these simulations, typically it's not. Look, if it's a cosmological constant, then there are no perturbations, even on large scales. And usually, well, I mean, these kind of simulations typically assume a cosmological constant, so you don't need to worry about this. But you have other simulations where they have dynamical models for dark energy, and then you can put them in that way. But these are typically on large scales, and usually linear perturbation theory is valid there, so you don't really need a simulation for that. I mean, the simulation is, and it's much faster to do analytical and the linear perturbation theory than the simulations would need. For that, you need a lot of computation. So these are more interesting for the nonlinear structure on small scales anyway, but we can still do it. So dark energy is completely integrated into this. Any other questions? Okay, and so by shooting the photons, and you get these typical maps, simulated maps like this. Okay, and then you can study the statistics of the shear field and try to characterize the shear field. We'll talk about that in a minute. But the first thing I wanted to mention is that one can already do a decomposition of the pattern of the shear field into different modes. That's what I was already described briefly before, so let me repeat. One can decompose any such, so you can take any such shear field, so any such arrowless vector field, or a massless spin-2 vector field, and you can show that you can always uniquely decompose it into two kinds of modes, or two kinds of patterns, if you wish. One is called E modes, and the other one is called B modes, in analogy with electricity and magnetism, where you can decompose the electromagnetic field into the electric field and the magnetic field. But here this is done in 2 dimensions for a spin-2 massless field. So it's an analogy, but has nothing to do with electric field and magnetic fields. But the point is that the E modes have no handedness, and so they're invariant if you under parity. So if you look at them in the mirror, it looks the same. Well, the B modes have a handedness, and so they change patterns as if you look at them in the mirror. And one can show that one can uniquely decompose an arbitrary shear field like this into these 2 modes. So you can take a shear field like this, and then do a transformation and get 2 maps, one for the E modes, one for the B modes. Of course, in practice, if there's noise and so on, there's some degeneracy, but if it's noise-free, like in a simulation like this, you can uniquely do it. Now, the reason this is very important is because it turns out that weak lensing only excites E modes. So at least to first order, lensing only produces E modes. It produces very, very small B modes at higher order, but that's very, very small and negligible for most purposes. So really, weak lensing only excites E modes, which means that if we take a measurement of the shear field and do an E mode, B mode decomposition, one expects to see only E modes. Okay? And if we see B modes, it means that there are systematics to the measurement. Something went wrong in the measurement. So the decomposition between E mode and B mode is a very strong test of the analysis and of systematics. In general, there's no reason why systematic effects would not produce B modes at all, right? I mean, this is a very special property of lensing. And in fact, it can be traced to the fact that the weak lensing arises from a scalar field, which is the scalar potential, which is the gravitational potential. So the fact that only excite E modes can be traced to that fundamental fact about the lensing. So you see, it's very special. And so the E and B mode decomposition is a very interesting and powerful test of systematics. And I'll be coming back to that later. And as I told you, this E and B decomposition is mathematically identical to the E and B decomposition that people do for the CMB polarization. In fact, the CMB polarization also can be described by such an arrowless vector. And the math of the analysis of the polarization is identical to the math of the analysis of the shear field. So that's also convenient. Okay. All right. So now let me talk about how one can characterize the statistics of this field. Right. So if you have a measurement of the shear, okay, one can imagine we can, as I told you before, we can take the shear field, invert it, and make a mass map. That's very interesting. You can look at the map. You can see where the structures are. You can compare to the baryons. You can do astrophysics, and so on. I'll show you some of the actual measurements a little bit later. But for cosmology, what's even more useful is to characterize the statistics, the statistical properties of this shear field, and compare it to models of structure formation, and from that constrain our cosmological model and measure cosmological parameters. Okay, so then we need to be able to find statistical measures for that characterizes such a shear field. And there are several that have been introduced. The lowest order statistics are called 2-point statistics. Okay? And they characterize how much clustering, or how much fluctuations there are as a function of scale by taking products of shears at 2 points. Okay, so an example is given here. with the shear power spectrum. So in this case, you can imagine taking a Fourier transform. So you have the shear field, which is generally a function of position. So gamma is a function of theta, which is a two-dimensional coordinate system on the image. You can take a two-dimensional Fourier transform. Let's call the modes L. Okay. Then what you get is the Fourier transform of the shear. So let's call it tilde, gamma tilde, which is a function of the Fourier mode L in 2 dimensions. And then you can take the product of the Fourier transform of the shear for one L, and then the Fourier transform of the shear for another L. Let's call it L prime. And then you can average over all available modes in some bins in L, for example. Or more theoretically, you can average over random realization of the field. And you can show that the field is statistically homogeneous and isotropic, so it's invariant under translations and rotations, at least statistically. So there's no special place, no special direction. Then you can show that the average of the product of this Fourier transform of the shear field can be written as a delta function, which involves L minus L prime, times a function which depends on L, which is called the power spectrum. In this case, it's the power spectrum of the shear. And what you get basically is a function which depends on L, which corresponds to inverse scale. So it tells us how much power there is as a function of inverse scale, which is equivalent to saying how much fluctuations there are as a function of angular scale. And this CL is exactly the same as the CL you get for CMB polarization. I showed you plot in the first lecture of the measurement of the CMB polarization as a function of L, and it's exactly the same, mathematically the same quantity. Now the nice thing about the shear power spectrum is that we can relate it directly to the power spectrum of the density fluctuation. So we can show that this shear power spectrum can be written like this. Okay, it can be written as some constants, which includes some cosmological constant, like say the Hubble parameter omega matter squared, times an integral along the line of sight of a weight function, where you can see the old weight function that we introduced to define in our lensing equations. So that depends on the redshift distribution of the sources and some angular diameter distances, and there's some other ones here, times the power spectrum of the density perturbations. So Amjan will describe this, but basically this is the power spectrum of density perturbation taken in 3 dimensions. So you take the box that I showed you, you do a Fourier transform, take products of the density power spectrum of the density Fourier transforms, and you get a power spectrum that depends on scale here, and it also depends on time, because as you see the box in the simulation of the box, the structures evolve as a function of time. So you integrate this along the line of sight, including the evolution as a function of time. So what it means, more physically in simple terms, is that this lensing power spectrum, so if we can measure the shear, okay, and compute the power spectrum of the shear, then what we're measuring physically is, apart from some constants depending on cosmology, and then it's basically a projection of the 3-dimensional density, a matter power spectrum of matter densities weighted by some weight function which we know and also depends on cosmology. So what we're getting is a projected, basically a projected version of the matter power spectrum with a window function, in a radial window function, which is given by this and this is. So really what we're measuring directly is the power spectrum of matter fluctuations projected. Right? And the projection depends on the redshift of the galaxy, so we can look at galaxies at different redshifts and regain some 3-dimensional information from this. I'll be talking about this a little bit later. Okay, so that's one form of 2-point function, and these 2-point functions are to lowest order what can characterize the statistical of the shear field as a function of scale. So how much fluctuation there are as a function of scale. Now there are other 2-point functions one can do. A simple one is to look at the correlation function. So you can take the measurement of the shear at some point and the measurement of the shear at another point, separated by an angle theta, and then you can average over all pairs, so maybe it's easier to look at this. You can look at the shear measured at some point here, the shear measured at another point here, so the shear is a little arrowless vector at this point. And let's say these 2 points are separated by an angle theta. Then what we can do is we can take the product of the shear at this position times the shear of this position and average over all pairs of points or all pairs of galaxies which are separated by this angle theta. Okay? So we make an average of all pairs separated by the angle theta, and then we can compute what the product is, and then we can look at pairs separated by another angle, do it again and again, so we get a function which depends on the separation theta. And that gives us another 2 points. So again, it's a product of two shears. It's the average product of two shears, just like we had in Fourier space in this case. And that's another way of characterizing the correlation function, the 2-point function of the shear. In fact, it turns out that, and you can form several ones because the shear has several components. You can also do an EB decomposition here, for instance. I'll talk about that a bit more later. And it turns out that some combination of these correlation functions are actually the Fourier this is the correlation function in real space. This is, in some sense, the correlation function in Fourier space that we call the power spectrum. It turns out there's a very nice relation between the power spectrum and the correlation function. Basically, the power spectrum is the Fourier transform of the correlation function, and the correlation function is the Fourier transform of the power spectrum. So they encode exactly the same information. One is in Fourier space, one is in real space. And they have different properties which are interesting when it comes down to noise. And so sometimes one chooses this, sometimes one chooses that. I'll come to that a bit later. There are other ways of characterizing the 2-point function of the fluctuation as a function of scale. At early times, we didn't have much signal, so we used something even simpler. So what we did is we drew a circle on the sky of radius theta, and we measured the average shear in that circle, and then we displaced the circle somewhere else, measure the average shear, measure the average shear. So we measure the average shear, square it, displace the circle, measure the average shear, square it, measure the average shear, square it, and basically average, take the average of the square of the shear averaged inside this circle. So it's basically we're smoothing the shear field with a circle of a given theta and computing the variance of the shear inside a circular aperture and calculating the average. There's a nice relationship between the power spectrum and this so-called shear variance in circular shells. It's basically an average of the power spectrum over an integral of the power spectrum over L with some weight function, which is the Fourier transform of a circle, sorry. And this has the advantage, so it's no longer used very much, but when we had very little signal because our area of survey is very small, the advantage is that we're basically averaging over many Fourier modes, so we're getting more signal for a given theta. Okay, so in some sense we're adding a lot of signal as a function of theta. The disadvantage is that the measurement at different thetas are all correlated because we're averaging over, there are a lot of common modes in it. So we're getting very correlated measurement at different thetas, but at early times that was still better to do. And now people tend to use the correlation function or the shear power spectrum. There's another one that was introduced, which is quite interesting. Instead of averaging over a circle, which in 2 dimensions will be a top hat circle, so it's 1 inside radius theta and 0 outside, one can also look at more interesting weight function. So if we look as a function of theta, the circular aperture will look like this, so constant and a 0. Okay. One can also do an average with more complicated apertures. This is one that has been proposed called the mass aperture, which is interesting, which is basically a compensated filter, so it's positive at some inner radius and negative on the outer radius. And one can look at the average of the square of the shear average with this mass aperture. And the advantage, there's a number of very nice properties of this mass aperture. One of them is that because it's compensated like this, it decorrelates very fast. So here, there's a characteristic angle theta, which is let's say the first 0 of this aperture. And if you start looking at the correlation of two mass apertures separate by an angle theta, when it gets larger than this characteristic scale, then it decorrelates very quickly. The other advantage is that you can also relate the shear field and the density field, or the convergence, very nicely with this formalism. We won't talk too much about it, but that's an interesting way of characterizing the shear field. But if you take the square of the average of the mass aperture, it's just another 2-point function, and you can also express it in terms of the power spectrum, and it's simply another, it's an integral also of the power spectrum over L times another weight function, window function, which is the Fourier transform of this aperture. So it's always related to the power spectrum. You can always relate all of these to the power spectrum. This would be the Fourier transform of the power spectrum. So another integral over L. Okay, so these are just equivalent ways of characterizing the shear field with 2-point statistics. Now, if the shear field is Gaussian, that's all the information there is. All the information is encoded into the 2-point function. If the shear field is not Gaussian, then you have extra information. We'll come back to that in a minute. Yeah.
So last time you said that the way you infer that there is a distortion by lensing is by studying the shapes of galaxies in a given pixel.
Yes.
And then you say you notice some correlated distortion. So this calculation of shear is coming from statistics, like studying multiple galaxies in the same pixels and seeing correlations. And then you are studying the statistics of this quantity, which is derived from.
I think I see what you said. That's a very good question. So, previously I said we look at a small patch of the sky, we average the shapes of galaxies, and we get a measure of the shear, and then we do it in another pixel, and so on and so on, and we get a pixelized version of the shear. Okay, but we average on some pixel size. And then the question, how does it relate to these statistics, right? So one could take the correlation function of the values of the shear in these pixels. You can imagine you take one pixel, look at take the shear in that pixel, the shear in another pixel, separated by some angle theta. Take the product of these two shears, and from these correlation functions, and that would work. The only thing is that the shear field then has been smoothed on the scale of the pixel. So what you would get is a smooth version of this power spectrum. You get the same power spectrum, but on small scale, it will be smooth, it would be suppressed by the window function of that pixel. So in practice, we don't do this. We go directly to galaxies. So we take, to compute these 2-point functions, we don't pixelize. We don't pixelize and then take the 2-point function. We directly get the 2-point function of the galaxy. So we take one galaxy here, and compute the correlation function of the two galaxies. And the way we do it is we turn the shape of the galaxy into an estimator for the shear for each galaxy. Okay. So what I was telling you before is to try to give you an explanation of how one can map the shear. But to map the shear, we'll still do pixels and average over pixels. But here we actually skip that step and go directly into the correlation function of the shear evaluated at every galaxy. And I'll tell you later how we do this, actually. So what we can get is an estimator so we can take the shape of the galaxy and get an estimator for the shear. It's very noisy, but it's an estimator. So we can either take an average of estimator and calculate the mean shear in a pixel, or we can take it and directly get the 2-point function of the shear from this estimator. Okay, you'll see when we do this. This is a crucial part of the analysis I'll come back to.
Sir,
yeah.
When we are computing CL by projecting from matter power spectrum, we are taking K as L by R.
Yes, that's right.
When R equal to 0, there is singularity.
Yes, when R is equal to 0 is singularity. Anyway, this G function at R equals 0 is 0. So this window function here, remember that enters the lensing calculation, anyway goes to 0 when chi goes to 0. So that singularity is in practice doesn't happen because it's suppressed. But in principle here, if this didn't go fast enough to 0, when chi goes to 0, you get a singularity. But this g actually goes down fast enough that this is finite. Yeah.
Is it the shear that you decompose into the E's and the B's?
Yes.
Yeah, then that the quantity which you are defining, the gamma I, the summation in the first one.
Yes.
So, aren't you like using spin 2 quantities and you're defining the CL?
Yes. So that's actually a good point and a subtlety. So they're really actually, you can actually consider 2 power spectra. You can take your shear field, decompose into E and B, and then you get a CL for the E and CL for the B. Here I'm skipping that step, but really this one is the CL for the E modes. You can also show that if you are lensing only and no systematics, you can calculate the CL for the B mode, and it's extremely small. All right, so it's we
and the Q's,
zero.
The Q's and U's you have in the mass aperture statistic. Are those the
these
Stokes parameters?
No. So no. That's completely different. The U is the window function, and what you can show is that the mass aperture average over this window function. So if you take the shear and average it with this window function, the nice thing about it is that it's also equal to the kappa, which is the density contrast, dimensionless density contrast, multiplied by another window function, which is related to the U. So you can take this one, do a transformation, and you get another one. And so you can also relate it to the average of the kappa. That's the nice thing about it. So you can measure this from the shear alone, and you mathematically get a measurement of the kappa average over another window function, which can be calculated. Yeah. But you're right. Actually, here you could, because you have 2 components of the shear, you can combine them to get several power spectra. It turns out there are 2 independent ones, and usually the E mode and the D mode. So here I'm talking about the E modes. Similarly with the correlation functions, you have several correlation functions, so you can do a transformation and get an E mode correlation function, a B mode correlation function. If I show you measurement of that. Any other question? Okay, so for a given cosmological model, one can do perturbation. We can calculate the background evolution. We can calculate the perturbation theory, which is what you're doing with Anjan and the process doing with Anjan. If you want to go into small scales and go to nonlinear regime, you can do an Endbody simulation. And what that gives you is all these distances. Okay, so first the cosmological parameters, you have to choose them. So for a given cosmological model, one can compute all these geometrical quantities, and we can compute the power spectrum as a function of redshift. We can integrate it and compute the lensing power spectrum or any of these statistics. And these will depend on the cosmological model. So I can show you some of the calculations. So for instance, you can look. In fact, that's from that review I gave you. The circular aperture, the variance of the shear in circular aperture. So this measure here as a function of scale for different cosmological model. So the more favored one right now is lambda CDM, which is a long dashed line. This assumes that the galaxies are all at redshift 1 for this particular calculation. It could be more complicated or more general. It can be done also for more general distributions as well. And you see that for lambda CDM, you get this kind of curve, all right? So this is the shear variance in circular aperture of a radius theta, and theta is in the x-axis, right? So what you see is that if you go to small scales, you get more shear variance, and as you increase, you smooth out the shear more and more, and the variance goes down. So you get less and less signal. You notice that at a few arc-minute scale or so, this has units of, so this is actually the square root of the variance, okay? So this is the variance, the square root of the variance, so this has units of shear. And so what you notice, and this is in percent, so you notice that a few arc-minutes also, you get a few percent shear. So the tip means that, as I was telling you before, the typical shear, okay, if you take the variance squared to the square root, on a few arc minutes is about a few percent. Okay, that's what I was telling you before, so it's a very weak signal. And then another thing which is interesting is that you can also see what linear perturbation theory would tell you. So let's suppose that we evolve structures only through linear perturbation theory. We didn't do our simulations to see how structures form. We assume linear perturbation theory holds at all redshift. It's not correct, but we can still do it analytically. And you would get then this curve here. All right? And you see that these curves agree with the full calculation on large scale, so above about 10 arc minutes or so. The two agree. So if you look at large scales, we can only do linear perturbation theory, which is semi-analytic. You can get it from these codes that I described yesterday. But if you want to look at small scales, which is of course very interesting, there's a lot of information there, then you need to take into account nonlinear perturbations. And in these codes, like the one I was showing you yesterday, like iCosmo and many others, that can be included as some fitting functions to numerical simulations that allow you to get the nonlinear correction and get the full analysis. I show you the linear power spectrum and the nonlinear power spectrum. For the matter power spectrum, same thing for the lensing. Okay, you can also look at the shear power spectrum in different models. So this is shown here. So this is L. This is CL multiplied by L times L plus 1 over 2 pi, which is kind of a convenient convention. And then for the lambda CDM model, which is the one of interest now, is the red one. So here is the shear power spectrum that you expect. Okay, again, it goes up and goes down in with this convention. And again, you can compare to what you would expect from linear perturbation theory only. And if you turned off nonlinear perturbation, only did linear, you would get this. Okay, so once again, on high L, which corresponds to small scales, you get the answer completely underestimated. So the nonlinear correction is very important. But on large scales corresponding to small L, then you get a good agreement. Okay. Now, the reason why this is interesting as a convention, L times L plus 1 CL over 2 pi, is that basically to compute the variance here, all you need to do is integrate this quantity. So it turns out that the variance is the integral over L of this quantity here. So basically this gives you the value on this curve gives you the contribution per log L interval of the power spectrum to the variance. What it means is that if you take a value, let's say here, you see that if you go to L of 10 to the 4, it corresponds to a few arc minutes or so, then you read the value is of order 10 to minus 4. It means that the variance is about 10 to minus 4, which means that the square root of the variance is about 10 to minus 2, which is a few percent. Okay? So here you basically get something on the scale of the square of the typical shear signals that you expect. And if you change the cosmology, you get completely different results. So if you remove, so this is old models that are now ruled out, but if you take the same model, but for instance, remove the dark energy and replace it with matter, you get the dark curve. If you take the same lambda CDM and turn off the dark energy and leave it and replace it with curvature, you get the blue curve, and so on and so on. So clearly, these statistics depend on cosmological parameters. So by measuring these power spectra, then you can constrain cosmology. Okay, so that's one. The major piece of information is by measuring this 2-point function. Now one can do more. Okay, there's more information than that. So in the CMB, you have mostly the one map, and you can measure the power spectrum. It's mostly Gaussian, so that's basically most of what you can measure. There's actually more, but that's more advanced. But most of the information is coming from one power spectrum. But here it's more complicated because first of all the shear is non-Gaussian, the field is non-Gaussian, so you have information beyond the 2-point function, beyond the power spectrum, and also we have 3-dimensional information too, right? So we can get power spectra for galaxies at different redshifts. So let me talk about these two, which gives us further information. So the first one is about a 3-dimensional information. So what we discussed until now is a situation where we have the observer here, the structures that we want to probe, and then a galaxy at some redshift. Let me see if this works. Yeah. And then the galaxy at some redshift. But what we can also do is consider galaxies at different redshifts, right? We can imagine selecting galaxies which are at a different redshift. We can take a subset of galaxies centered on some redshift Z1. We can select them to be around redshift, let's say redshift 1, for instance, and do our lensing analysis with these. And then we can take another set of galaxies, let's say redshift 1.5, and do our lensing analysis again, and we're going to get two different power spectra. You notice that the light goes through partially the same structures. So these galaxies will probe structures around here. These one will probe structures on average at slightly higher redshift, but some of the structure will be in common, so there will be a strong correlation between the two. But nevertheless, there's three-dimensional information encoded in this if we look at this redshift analysis. And that's what we call weak lensing tomography. So each of them that doesn't give independent three-dimensional information, but by combining them, you can recover some three-dimensional information, a bit like tomography in medicine and so on. Okay.
So galaxy at higher redshift is distorted more rather than the with lower redshift, no?
Yes, it's distorted by these structures and more. And it turns out that indeed the signal is stronger as you increase the redshift of the galaxies. That's right. So each of these, so this G function, which is the lensing efficiency function that enters the calculation, typically what it does is a very broad function that peaks halfway between the observer and the galaxy. So if you looked at the lensing efficiency function or the window function, the lensing window function, for this galaxy, it would go like this and go back down. It would peak around the middle. And the lensing efficiency function of this one would also be broad, peaks in the middle. It would peak at a slightly higher redshift. But there's a lot of overlap, okay? So these two would give us some correlated information, but nevertheless, as I said, you can sort of deconvolve this and recover some of the three-dimensional information. I can show you how in this next slide. So for instance, if you compute the lensing power spectrum for two sets of galaxies. So you take your redshift galaxy survey, and then you divide which are median redshift around 1 or so, and then you divide the galaxies into two subsamples: the galaxies with redshift below 1 and the galaxies with redshift greater than 1. And you calculate the weak lensing power spectrum for each of these subsamples. Again, this is a theoretical calculation, not a measurement. Then you get the two curves. So again, the more relevant one, let's say, is the blue curve. So for the one at lower redshift, you get this blue curve, and the one at higher redshift, you get this upper blue curve. And you see indeed that the amplitude of the lensing power spectrum is higher for the galaxies at higher redshift. Okay? For a number of effects, it turns out. Both because you're doing through more structures, the structure formation also plays a role, but more importantly, it's actually these radial functions and these radial weights that happens to be higher for the one that are higher redshift. So if you split the samples into two, you can measure two or more. You can split more. You get 3, 4. You can measure different power spectra. They have different amplitude, different shapes. Okay, and then you can measure cosmological parameters. So, for instance, this is a projection for one survey. The error bars are projected to be of that size, the light blue. You can imagine measuring both of them and constraining cosmology. And in particular, one of the things we're interested in, of course, is constraining the dark energy parameters, in particular the dark energy equation of state parameter, W. So the blue line assumes 30% of dark matter, 70% of dark energy, and a W corresponding to a cosmological constant, which is W equal -1. But let's say you consider the same model, but now W is equal to -0.7, so 30% smaller. It's quite a big difference nowadays, but just to illustrate the effect. Then in that case, you would get the light green curve. Okay, so you see, there's a difference. It's not a very big difference, even though we've changed W quite a lot. but nevertheless a difference. So if we can measure these two power spectra with the precision given by the light blue, then we can hope to constrain W. But you see that W is a parameter which doesn't have a very big effect. So it's hard to measure. And now the current constraint on W are about between 5 and 10%, which is much less than this. It's about 30% change, so about a third of this or more. And in the future, we're targeting 1% error on W. So you see, we correspond to very high precision in the lensing power spectrum. And again, I'll come back to that at the end. Okay, so this is what we gain by adding the redshift information, the three-dimensional information. It turns out that you can try to see how much you gain by splitting the galaxies into 2 redshift bins, or 3, or 4, or 5, or 6. It turns out that by subdividing more and more, eventually you don't gain much, because the lensing window function is so broad that you basically don't have that much more three-dimensional information. And typically beyond 3 or 5 bins, you get most of the three-dimensional information out. But you get a big improvement in your cosmological constraint by going from 1 to 2. Slightly smaller but still significant improvement by going from 2 to 3, and then 4 and 5 you get less and less, and eventually you don't gain very much anymore.
Sir, is there any angular size limit, angular limit for the galaxies, like from 1 to a second, like angular limit, or if we can get tomography?
What do you mean angular limit?
2 galaxies are separated by some angular distance.
So no, because what you do is you take your galaxies, you have your galaxy sample. They have a broad redshift distribution. In fact, I was drawing it here. So if you have a galaxy, you take a galaxy sample, a galaxy survey, and you plot the number of galaxies as a function of redshift. Okay, let's say it has this distribution. Okay. Then what you do is you just take your galaxy sample and you take the galaxies at low redshift and the galaxies at high redshift and you split them. And then you get, let's say, one is distributed like this, the other one will be distributed like this, let's say, or more like this. And then you do your lensing analysis for this subsample and this subsample. Okay, just as if you didn't know about the other one. So that you can still look at all scales, all angular scales.
Okay, so this is done by third.
This is a theoretical calculation.
Linear, it includes linear.
This includes nonlinear corrections. Yep, this includes nonlinear corrections for the two subsamples of a galaxy survey separated into 2 in this case. Now, one thing one can also do, which I didn't have time to mention, but it's interesting. So you can do the power spectrum of this. So let's call this the sample 1. Let's call it the sample 2, right? You can take the lensing power spectrum for the sample 1. You can take the lensing power spectrum of the subsample 2. What you can also do is you can do the cross-correlation power spectrum between 1 and 2. You can take one galaxy in one sample and another galaxy in another sample. Okay? So even if you split into 2, you really have 3 power spectra. And that's what people do. I'll show you results later. So, and that gives you additional information, which is very interesting. And if you have 3 subsamples, you have more than 3, you actually have, 5 power spectra, I think. Okay? And so on and so on. So you actually have a lot more than information than this. And this is all correlated, and it should behave in well-known ways as you change the cosmological parameters. So that adds a lot of information. Okay, so that's adding the 3-dimensional information. And another piece of information, which is also very important, is to look at the non-Gaussian nature of the field, right? So what does that mean? So we know that if you look at a simulation like this, because the structures have become nonlinear, initially the density field was Gaussian. So what is a Gaussian field? A Gaussian field is it's a statistical field. So you imagine you're in your 3-dimensional box, let's say, or maybe more simply a 2-dimensional field like this. What it means is that if you made many, many realizations of this field for different realizations of the universe, if you looked at 2 points on this field, you looked at the joint distribution function. Well, you look at 1 point in the field, and you look at the distribution function of the value of the field in different realization, you would get a Gaussian. If you look at 2 points, 2 random points, you look at the joint distribution function of the field, so the probability of the first one to have this value and the probability to have the other one to have this other value. Then you get a two-dimensional Gaussian. Could be an ellipse, but still a Gaussian. And for 3 points, same thing. You get a three-dimensional Gaussian, 4 points, four-dimensional Gaussian, and so on. Whatever number of points you take, if you make many realizations, then the joint probability distribution function of these random points are Gaussian. Okay, and for these, so these are very special kind of statistical fields. And you can show that for such fields, all the information is encoded in the two-point function. So if somebody gives you the power spectrum of that field, you know all the information, you can make many realizations, all the information is encoded in there. But in most fields, like let's say you take an image in this room and so on, it's not a Gaussian field at all. I mean, you have structures, you have texture, you have faces of people. I mean, this is not Gaussian in the least. So the simulation I was showing you before, in the cartoon simulation, it was a simple realization of a Gaussian field. So a Gaussian field, is smooth, has this kind of structures, but it doesn't have clumps like this. Okay. While in the Endbody simulation, which is a realistic one, where the photons are shot through real structures with filaments and clusters and so on, then you get a much more clumpy field. All right, and that means that there's at least more information encoded there's much more information that's given by the two-point function. You can measure the two-point function. I showed you how you can calculate it and so on, but that's not the entire story in terms of information. You can gain more information by looking at higher order statistics. Okay. And so people have come up with different kind of high order statistics, and many of them are tried and used and so on. A natural one is to look at 3-point statistics. So you go in higher order. So instead of taking the product of 3 shears or 3 kappas, they express in terms of kappas, but you can do it in terms of shear as well. Instead of taking the square of kappa and taking the average, you take a cube. All right, and you can normalize it by the average of the square just for convenience. That's going to probe how Gaussian the distribution is. All right, and that's called the top hat skewness. In this case, it's with the top hat window function like we did for the two-point function. You can form this, and that's one of the statistics. You can do the same thing with the skewness. With the mass aperture. So this is called the skewness, by the way. You can do the skewness of the mass aperture, same thing, taking the cube of the mass aperture. You can also look at high order shear correlation function. You can take, instead of taking the product of 2 shears, you can take 3 or 4. Another possibility is to look at the full probability distribution function. So you can look at the value of the shear in let's say a circular aperture. Take it, move the aperture, look at somewhere else. You can build a histogram and look at the full shape of the histogram. If it's non-Gaussian, it's not going to be Gaussian, and you can study the shape of that distribution. Okay. Another very interesting one, which is now being pursued very actively, is to look at so-called peak statistics. So peak statistics consist of detecting. So you see most of the shear signal is coming from these clumps, which are galaxy clusters, actually, which are the intersection of these large-scale filaments. So one thing you can do is you can detect the peaks, and you can count them, you can measure their amplitude, their shape, their correlations, and so on, and hope to capture a lot of the non-Gaussian information which is coming from the clumpiness. It turns out to be a very powerful statistic, the peak statistics. So a lot of people are pursuing this as well. And what's even more fun is that you can also do it for galaxies at different redshifts. So you can do non-Gaussian information, tomographic, right? You can take your 2 samples, the low redshift, high redshift, and then look at your non-Gaussian statistics at different redshifts. So you see you have a lot of information to use, okay? And that's currently a big area of research, how we characterize all this non-Gaussian information. So a lot of people the community spent a lot of time to learn how to analyze the cosmic microwave background maps and measure the power spectrum. And now the next step is to characterize fields which are non-Gaussian and three-dimensional. And there's still a lot of work to be done there to capture all the information. Yeah, the question.
So when you say the cosmic shear field is non-Gaussian, do you describe it as some deviation from a Gaussian field, or do you not look at it as Gaussian entirely?
Yeah, so it depends on the scale. So we saw that if we go to large scales, it's Gaussian. And we go to very small scales, it's heavily non-Gaussian. It's more and more clumpy. So there are different ways. So you can look at mildly scales which are not too far from large scales, so not too nonlinear. And there you can start doing nonlinear perturbation theory to higher order. It still converges. And there it's very useful to look at deviation from a Gaussian. When you go to the mildly nonlinear regime, it's very non-Gaussian. And then there are other distributions that are better. So it turns out, for instance, log normal distribution is a good description in a very nonlinear regime. It turns out, so you can look at that. Or you can just look at these peaks. I mean, looking at these peaks is a way of, it's basically the fact that the tail is very long. You have what does gravity do, right? It makes the structure collapse, as I show you in the simulation. It means that some regions becomes very empty, and some regions collapse into these very dense regions. It means that the distribution has a very long tail. And why is it non-Gaussian? First, because there's a long tail, but also because a region which is empty cannot be more empty than completely empty. So it cannot have a tail on the other side, right? So it's a very skewed distribution. I mean, when you look at it, and this is generic of gravity, of structures being driven by gravity. You get, in an expanding universe, you get this very generically. So you start with, so if you look at the density contrast, so delta, which is basically the density minus the average density over the average density. If you look at early time, the distribution, so this is the probability of this density contrast. At early time is Gaussian. Okay? It's Gaussian and, well, I should draw it like this. It's Gaussian and very narrow because the fluctuations are very small. And then it grows. So as time goes on, it becomes, you get more and more structures, but it's still linear. And eventually, it becomes, some of it becomes nonlinear. So on the scales that become nonlinear, basically you get a very skewed distribution, something like this. You know, it's kind of cut off here and has a very long tail here. And the tail corresponds to galaxies, clusters of galaxies, and so on. And here on the distribution on the other side corresponds to voids. And the fact is that you cannot have, as I said, something more negative, more empty than the void. So it's cut off. So that's why it's naturally completely skewed like this. That's why when you measure skewness and so on, which measures how skewed the distribution off from symmetry, you can start capturing some of the information.
So roughly, what is the scale at which you can no longer treat it as a deviation from Gaussian?
That's a deviation from. Well, I mean, it's linear now on scales of about, as I showed you before. So here. So basically, be above 10 arc minutes, it's still linear. So then the Gaussian is still a good approximation. And then the nonlinear starts coming in later. So here it's no longer Gaussian, and perhaps here you can do some perturbations around the Gaussian, for instance. But again, it's not a close problem how to fully characterize this field now. Okay, and it's both difficult because non-Gaussian, but also very interesting. Yeah, and it's nothing is. Whenever something is interesting, usually it's not easy. But fortunately, if it's really easy, it's been done already. So, all right. Now, what's interesting is that, from the cosmological point of view, it was shown by Bernardo and collaborator early on that one can get more cosmological information from these higher order statistics. In this case, they considered the skewness, the 3-point function, and they showed that you can break degeneracies which are present if you only measure the 2-point function. So if you measure 2-point function, you're going to get some strong uncertainty in certain direction of parameter space. And if you include the 3-point function, you can break this uncertainty and get more information. So there's quite a lot at stake in trying to characterize the fields with these non-Gaussian statistics. But as I'll discuss later, it's actually they're even harder to measure, because if you think about it, the shear is of order 10 to minus 2%. The 2-point function is 10 to minus 2, 10 to minus 2, that's 10 to minus 4. If you want to do a 3-point function, for instance, that 10 minus 2 to 10 minus 2 to 10 minus 2, that's 10 minus 6. So the signal is even lower, and even worse for the higher order. So the signal in these higher order statistics is lower, so they're harder to measure. So for the moment, the measurements from higher order are not very constraining. But when the surveys become larger and larger, the signal becomes, we have more and more signal to noise, and then we will start to be able to do this. Yeah, you have a question?
So as we go to smaller and smaller scales, would we require higher order functions? Like go to slightly smaller scales, you need 3-point functions, and then you need 4-point functions.
Yeah, unfortunately, it doesn't work. So if you look at linear scales, and the 2 points enough, and if you go to slightly smaller and smaller, you can do you can still do perturbation theory, okay? And you can go to higher and higher. However, beyond a certain point, when you get to the very strongly nonlinear regime, that expansion doesn't converge. And so strictly speaking, all the information, if you have all the correlation functions, you can get all the information, but it converges very slowly, and so it becomes very inefficient to do it like this. And in fact, that's still, people have, that's why, for instance, analytically, one is not capable, nobody is capable of computing the power spectrum in the nonlinear regime, because the perturbation theory fails, unfortunately. And so that's an open problem. That's why people do numerical simulations. Nobody has managed to do it analytically. And it's related to the long-range nature of gravity, somewhere, that this perturbation it's non-perturbative. So you cannot do this calculation perturbatively. So you can do it in a range of scales, and eventually it doesn't converge. That series doesn't converge well, and it doesn't work anymore. So you have to use other techniques. But this is a very interesting fact, and also a lot of research continues to. If somebody manages to compute the 2-point function analytically in the nonlinear regime, that would be a big breakthrough. But for the moment, nobody has done. There's a lot of approximation schemes. A lot of them are based on physical principles. There's even field theoretical techniques that are now applied for these things. But for the moment, there's no analytical description all the way into the nonlinear regime. Okay, I think it's time for lunch.
But I think due to this difficulty also, but one has to consider nonlinear regime, no? It is necessary. What is your opinion about this?
Well, there's a lot of information in the nonlinear regime. So if you don't want to do this, you have to stick to large scales, which is a pity because you're missing all this small scale information. So in very big surveys where we have a lot of scales available, we can afford not to look at nonlinear scales, small scales, but there's still a lot of interest in also including the nonlinear scales. So for the moment, we use the nonlinear scales, and we use Endbody simulation effectively, or fits to Endbody simulations to get the result. I mean, the Endbody simulation work well, right? It's just that analytically it's not possible, so it's very heavy to run a large number of Endbody simulations, but that's what we do. So yes, we do want to get at these nonlinear scales. And we're going around the fact we can do it analytically by doing Endbody simulations. All right, so it's time for lunch. So this next time I'll tell you about how we actually measure shear in practice, which is now the questions we're getting from different angles. And then I'll tell you about the latest observational results and the future.